In this lesson, we're going to be looking at rate laws and order of reaction, so the experimental determination of a rate law. Just to recap, in the previous lesson, we learned that overall chemical reactions are made up of a series of smaller chemical reactions called elementary steps, and all those elementary steps put together is the reaction mechanism that produces the overall reaction. The rate law is the mathematical equation that will tell us how fast a reaction is going, or rather how fast a reaction will go based on the concentration of reactants. So, rate laws can be easily predicted for any reaction mechanism. You can create a mathematical equation for the rate of a reaction if you have the reaction mechanism, because all you need to do is look at the rate determining step, which is the slowest step in the reaction mechanism, and write the rate law for that rate determining step. You cannot, however, write the rate law from a balanced equation unless that balanced equation is an elementary step. Rate laws, as we learned in the previous lesson, must be determined through experiments. So through experimentation, we can derive a theoretical reaction mechanism that will allow us to create a mathematical expression, a rate law, for how fast a chemical reaction will go based on concentration of certain reactants. There are two forms of the rate law. And the first form of the rate law is called the differential rate law. So, differential rate law. And it indicates how the initial concentration of all the reactants affects the overall rate of reaction. There is also something called the integrated rate law. The integrated rate law indicates how one specific reactant or product concentration varies with time. We will only be studying in this course the differential rate law. Differential rate laws, they express how the initial rate of reaction depends on the initial concentration of reactants. So, consider the following reaction. So this reaction is not necessarily an elementary process. It's not necessarily an elementary step. We have X and Y reacting to form Z, where the lower case represents the stoichiometric coefficients. So the differential rate law is the initial rate of reaction based on the initial concentration of reactants. So remember that the rate law is typically given as R, the rate of the reaction, is equal to K, which is your rate constant, times, and in this case, the reactants are X and Y, so concentration of X times concentration of Y, and these will be raised to the exponents m and n. They are not raised to their stoichiometric coefficients because you can only raise the concentration of reactants to the stoichiometric coefficients if it is the rate determining step in a reaction mechanism. So let's make a little note of that, okay? Because that is often a point of confusion. You only use the stoichiometric coefficients as exponents in a rate law you only use stoichiometric coefficients as exponents in a rate law if the reaction is an elementary step in a reaction mechanism. Okay, for example, the rate determining step. The differential rate law, we're using the concentration of the reactants raised to some exponent, and that's the exponent that we are going to use experimental data to find. So we are going to use experimental data to find M and N. But we say that the order of the reaction, the order of the reaction with respect to X in this case is M. And the order of the reaction with respect to Y is N. And the overall order of the reaction is M plus N. The order of the reaction indicates the impact the particular reactant has on the initial rate of reaction and gives clues about the reaction mechanism. Recall that the rate law for a reaction can be obtained from the rate determining step of the reaction mechanism. So what does the rate order show? So if the rate determining step is simply species A colliding with the wall of a container, right, and then decomposing into products, then the molecularity is 1, where molecularity refers to the number of species that must collide to produce a reaction in this step. So in this case, all A has to do is it has to undergo some sort of collision, physical collision with a wall of the container, and then it will break up into products. Alternatively, it can collide with another species, right? But it doesn't necessarily need that other species to break up into its products. So the expected rate law is R is equal to K, and this reaction, right, because the rate determining step is A going into products, the reaction is, or the rate law is only going to be based on the concentration of A. Because if this is your slowest step in the reaction mechanism, then mathematically the rate of the reaction, or how fast the reaction goes, really only depends on the concentration of A. So the overall order of the reaction is 1. As you can see here, it's raised to the power of 1. So therefore, the overall order of the reaction is 1. If A must collide with itself in the rate determining step to produce a reaction, then the molecularity is 2, because 2 molecules have to collide in order for this reaction to happen. So our rate law, if it requires 2 molecules, then it is A to the power of 2. Because another way of writing that would be 2A goes to products. And because what I've just written here is a rate determining step, or because that what I've just written is an elementary step in the reaction mechanism, the stoichiometric coefficient is the exponent in the rate law. The overall order of this reaction is 2. If A must collide with B, then the molecularity is still 2, because 2 molecules must collide to produce products, or 2 species must collide to produce products. So we have R is equal to K. Now, the rate of the reaction is going to depend on both A and B, because this is the rate determining step, so we need both A and B present in order for the reaction to happen, or the slow step of the reaction to happen. So we say A and B. And the overall order of the reaction, and they're both raised to the exponent 1 because that's their stoichiometric coefficient, right? So the overall order of the reaction is the sum of those exponents, which is 2. If you have A plus B goes to products, then the molecularity there, so you've got 2A plus B, and the molecularity is 3. And you've got R is equal to K, A squared times B, with an overall order of 3. And in the final one, the molecularity is also 3, with R is equal to K, A, B, C. Note that typically we do not see rate determining steps beyond a molecularity of 3. And that's because it is unlikely that 4 species will collide at the same time with the correct geometry, right? So like colliding in the right spots with the right amount of activation energy in order for the reaction to happen. So we typically do not see rate determining steps with a molecularity over 3 because that is statistically very unlikely to happen, right? So at most you will usually see a expected rate laws at most to the overall order of 3. Now, suppose that experiments showed a rate law to be the rate of formation of C is equal to, so R is equal to K times A to the power of 1, B to the power of 2. Right? So we have this right here. I'll just rewrite that over here. R is equal to K, A to the power of 1, and B squared. If you doubled your concentration of A, okay, so we take A and we doubled this concentration, what effect would that have on the rate? Well, since A is raised to the power of 1 and we multiply the concentration by 2, then the rate will get multiplied by 2. So the rate would also double. So we would say that the rate doubles. Okay, so by a factor of 2. Now, if B triples, so if we tripled the concentration of B, well, that would mean that the whole rate would speed up by a factor of 9. And that's because we are tripling the concentration, which means then we have to raise it to the power of 2. So if B triples, then the rate would actually increase by a factor of 9, right? And so it would really speed up if you tripled the concentration of B. And that's because looking at this rate law, I know that my rate determining step will look something as follows. A plus 2B goes to form some products. That's the slowest step in the reaction mechanism. And since it requires 2 B species, if I triple that, well, that will really speed up the reaction because you'll have many more B species to react with A, and so the reaction will speed up quite a bit. There are 2 ways to experimentally determine differential rate law. We are only going to look this year at using data tables, okay, of initial reactant concentration and initial rates. So multiple trials of reactions are conducted, varying initial concentration of reactants, and the effect of the initial rate is analyzed. Okay, so here we go. You have this is an overall chemical reaction. I can tell it's an overall chemical reaction because I have 2 bromate species reacting with 5 bisulfite species to make all these products. So we know that this overall reaction is actually broken down into smaller steps in the reaction mechanism, and this data will give us some clues as to the rate determining step. okay? So it asks us to find the rate law. So if I looked at the differential rate law, that states as follows: R is equal to K, the initial concentration of bromate raised to some exponent, and then bisulfite raised to a different exponent. And again, what I'm going to try and do is I'm going to use the data to find these exponents, and then those exponents become the clues to tell me what's happening in the rate determining step. So what I will do is I will pick two trials. Okay, and I'm going to pick two trials in which we have a constant concentration of one of these species, right? So what I'll do is I will keep the concentration of bisulfite the same, and I will look at the difference of doubling the concentration of bromate and the effect that has on the rate of reaction. So I'm going to start by picking trials 1 and 2. Okay, I'm going to look at trial number 1 and 2. And the reason why I picked trial number 1 and 2 is because my bisulfite concentration in those trials stays constant. So I will only be looking at the effect of bromate. Okay, so what I'll do is I will actually set up an equation here. So the rate in trial 1 is equal to the K, the constant of proportionality, or the rate constant, bromate raised to the exponent 1, m in trial 1, and bisulfite raised to the exponent n in trial 1. Then what I'm going to do is I'm going to divide that by the rate from trial 2, the rate law from trial 2. So I'll divide everything, both sides, by the rate law from trial 2. Rate law from trial 2 is the same constant of proportionality, bromate, the concentration of bromate raised to the exact same exponent but from trial 2, and then bisulfite raised to the exponent n from trial 2. I'll insert some values here. So the rate of the reaction in trial 1 is 1.6. So I write 1.60. The rate in trial 2 is 0.80. I do not have the K value. The concentration of bromate in trial 1 is 4 raised to the exponent m. The concentration of bisulfite is 6 raised to the exponent n. Then I look at trial 2. K value again. Bromate concentration here is 2 raised to the power of m, and bisulfite concentration is 6 raised to the power of n. Looking at this equation, I can see that 6 to the power of n divided by 6 to the power of n, well, that's going to cancel. My k's will cancel. And then what I'm left with is 1.6 divided by 0.8. Well, that's equal to 2. And then I have 4 to the power of m over 2 to the power of m. Using my exponent laws, I can then say 2 is equal to 4 over 2 to the power of m. I can factor out the exponent. So 2 is equal to 2 to the power of m. Therefore, m is equal to 1. So I have now found this value, and that value, m, is equal to 1. I will do the exact same thing for the bisulfite. So I'm going to find two trials, right, where the bisulfite changes but the bromate stays constant, right? And that's going to be trial 2 and trial 3. Okay. So I'll find trial 2, 2, and 3. And now that you have seen how this works, I'm just going to go ahead and put rate 2 over rate 3. So 0.8 over 0.20. I know that the K values will cancel, and since bromate is being held constant, that will cancel. So then I'll only look at the bisulfite. So I will write here 6 to the power of n over 3 to the power of n. So 0.8 over 0.2, well, that's equal to 4. And I can factor out the exponent here. I can say 6 over 3 to the power of n. 4 is equal to 2 to the power of n. So therefore, n is equal to 2. Okay, and I have now found the exponent over here. N is equal to 2. So I actually can now write the rate law. The rate law is as follows. R is equal to K, the initial concentration of bromate raised to the exponent of 1, times the initial concentration of bisulfite raised to the exponent of 2. And this experimental data has now given me a clue as to the rate determining step. The rate determining step, because I now have these exponents, means that a species of bromate will react with 2 bisulfites in the rate determining step to make some sort of products. And with that clue, we can go ahead and maybe further derive a reaction mechanism. All right, but I know that since the reaction relies on bromate and also relies on bisulfite, but relies on bisulfite to the power of 2, I have a clue as to the rate determining step. How would you determine K? Well, K is actually fairly straightforward to determine. All you have to do is take a trial, any trial, insert values and isolate for K. So if I looked at trial number 1, right, okay, I would have 1.60 as the rate, right, and it's millimoles per liters per second. Millimoles per liters seconds is equal to the K value times the initial concentration of bromate, which I know is 4 millimoles per liter, times 6 millimoles per liter, then squared, right, based on my rate law that I have over here. Okay, so the rate 1.6 is equal to K, 4 millimoles, that was the initial concentration of bromate in the first trial. Initial concentration of bisulfite is 6 from the first trial, raised to the exponent of 2. Okay, and so then what I'm going to do is I will bring everything over to one side, right? And so this will end up being 1.60 millimoles per liters second, all divided by 4 millimoles per liter times 6 squared is 36 millimoles squared over liters squared, because the units have to be squared, is equal to K. And so therefore I can say K is equal to 0.11, 0.011, and if I look at the units, I've got millimoles, millimoles cancels, liters, liters cancels. This is the denominator of a denominator, so it moves up here. Okay, and so I will end up having liters squared over millimoles squared seconds. So I have the units of K and I have its numerical value. So write the rate equation. R is equal to 0.011 liters squared over millimoles squared seconds times initial concentration of bromate times the initial concentration of bisulfite squared. And finally, question D says, determine the initial rate of reaction when the initial concentration of bromate is 5.5 millimoles and the initial concentration of bisulfite is 2.1 millimoles. Well, you just insert those values into the equation. So R is equal to 0.011 liters squared over millimoles squared seconds times bracket 5.5 millimoles per liter and then 2.1 millimoles per liter squared. Okay. And so then you would calculate that. So that's equal to 0.267, I believe 267, let me just double check. Yep, 267 millimoles per liters second. And I know that's correct because my millimoles squared will cancel with millimoles squared. My liters squared will cancel with my liters squared. And then I will end up with millimoles per liter squared. We will not be doing from rate versus initial concentration of reactant graphs this year. So we will skip this information right here. And that should be it actually. So we are only covering this year the data tables of initial reactant concentration and initial rates. Thank you for watching.